Welcome to the Graphing Radical Functions podcast. All right, so first I wanted to go over those warm-up questions that you answered. Identify the domain and range of each function. Well, hopefully you remember that for polynomial functions, their domain is all real numbers. There's no number that we can't raise to a power or multiply some constant by or add something to. So the domain for both of these was negative infinity to infinity. Oops. Domain, we're still working on domain. Now the range, all right, so if you remember that if our leading exponent was an even number, right, so we were even degree, like to the second, degree 2 or degree 4 or degree 6. Right? Remember those functions, both of our ends go the same direction, right? The end behavior is both ends go to infinity or both ends go to negative infinity. So somewhere the function has to turn around. So because it turns around, it has a restricted domain. Right? Now if you couldn't tell what the domain would be by looking at it, you could always graph it. Right? So I have just a very, not very formal graph, just a rough sketch, just to give us an idea of what the range is off to the side there. And it's the first one here. This one here is sort of a rough f of x equals x squared plus 2. All right, so that would be a parabola. And basically it would just be our parent function, f of x equals x squared, shifted up 2. Right? So that means that the lowest number that parabola is going to go through is the number 2. So the range is going to be 2, and we're going to use a bracket because 2 is included, and then it's just going to keep on going up to infinity. Okay, so that one had a restricted range. But our odd degree polynomial functions, where the leading exponent is to the 3rd power or to the 5th power or to the 7th power, well, the ends go in opposite directions. So eventually every y value is going to be hit. So the range here is negative infinity to infinity, all real numbers. Use the description to write the quadratic function g based on the parent function f of x equals x squared. So f is translated 3 units up. We just take our parent function, f of x equals x squared, and if we're translating vertically, if the function moves up, we add that value, and if the function moves down, we subtract that value to the whole equation. So that means that this would have been f of x equals x squared plus 3. If we're moving left and right, it means we have to add to our x. Right? Oh, by the way, here, let's talk about our vertex. Our vertex for this graph would be 0, 3. It's basically just like that first parabola I have drawn there, except instead of shifted up 2, it's shifted up 3. All right, so, but our second one there, or our fourth problem there, if we're going to translate to the left, right, remember that we're adding that value to our x. Not to the whole function, but to the x. So this one was x plus 2 squared. And here our vertex would be negative 2, 0. Right? Our parabola has just been shifted 2 to the left. Well, how'd you do with those? Hopefully you did okay. And you'll get some more practice on Monday's lesson in working with translation. So if you had a little bit of trouble, don't worry, you'll get more chance to work on that. We're going to talk about, very briefly, radical functions, and specifically square roots and cube roots. So we're going to be graphing square roots and cube roots. And we're also going to be transforming those radical functions by changing the parameters. We're going to add something to the function or subtract something or multiply something to the function and change it a little bit. In the first part though, we're just going to graph our basic parent function. So first though, a little bit about those two parent functions. So square root and cube root functions are inverses of quadratic and cubic functions. The graphs below show the inverses of the quadratic parent function and the cubic parent function. And I have these in your notes as well, just so you can get a little idea of a function and its inverse. Now, something interesting about inverses, and if I didn't put this in your notes, add this part with the star. I think I didn't include that. So inverses are reflections over the line y equals x. And interestingly, x and y switch on the inverses. So if you remember back from geometry, when we were graphing reflections over the line y equals x, we switched the x and y. Okay? And that's because that's exactly what happens when we reflect over that line. And since our inverses reflect over the line y equals x, their x and y coordinates switch. All right, so first we have the graph y equals x squared. That's the blue graph. And then we have the reflection of that over that line y equals x squared. All right, so f, by the way, if you, over the line, excuse me, y equals x. If you aren't familiar with inverse notation, that -1 on the f does not mean f raised to the -1 power. It signifies inverse, right? So that -1 signifies inverse. All right, so now when we look at the red graph, which is the reflection of f of x equals x squared over the line y equals x, we can see it's not a function. Okay? It fails the vertical line test. Right? There's more than one y for each x value. Right? Remember, for a function, there has to be one and only one y given an x value. So if I give you x, you have to know which y to go to. And here, I don't know which y to go to, the positive one or the negative one. And it's actually very easy to write inverses, so long as it's an easy equation to solve. You simply switch the x and y's and you solve for y. All right, so here we have y equals x squared. And if we switch them, we have x equals y squared. Because on inverses, x and y switch. And now we want to write it as a function. We're going to solve for y. All right, so we'd have to take a square root of both sides. But remember, you have to take a positive and negative square root. And so now we have y equals plus or minus the square root of x. And that gives us not a function because we actually have two equations there. All right, so we have a way of dealing with that for the square root. The cube root, however, is a function. The blue graph is f of x equals x cubed. And then the red graph is the reflection of that over the line y equals x. Of course, again, that f negative 1 x equals the cube root of x, that just signifies inverse. And the cube root is the inverse of cubing, right? That's the inverse operation. If you want to eliminate a cube, you take the cube root. If you want to eliminate the cube root, you take a cube. Right? And here we can solve for one equation. And that 3 looks awful big. It's supposed to be the index on the radical. So to find the equation of the inverse, right, we just switch the x and y, and we have x equals y cubed. And then we take the cube root, and there isn't a plus or minus on a cube root. There is only one solution anytime you're taking a root and it's an odd index. And so y equals the cube root of x that still looks like times 3. My index is a little large there. So y equals the cube root of x, I'm going to write that one more time, is the inverse of y equals x cubed. Let's see if I can write it really tiny now. Maybe if I make the x really big. Okay, there, that looks like cube root and not 3 times the square root of x. All right, so let's see what we're going to do about that square root there. That's not a function. Right? So since the inverse of y equals x squared is y equals plus or minus the square root of x, which is not a function, fails the vertical line test. There's not just one y for every x. If we just restrict the domain for y equals x squared, for x values greater than 0, we're going to have a function. So this restriction is made so that the inverse will be a function. All right, so now if we only look at half of y equals x squared, its inverse, y equals the square root of x, is indeed a function. And what we're going to be graphing is our functions. So just a little background on the relationship between the radical functions and their inverses. So a radical function is a function whose rule is a radical expression. It has to have a radical in it. Makes sense, right? So a square root function is a radical function involving the square root of x. The square root parent function is f of x equals the square root of x. The cube root parent function is f of x equals the cube root of x. And those are the only two radical functions we're going to be graphing. And as a matter of fact, that's what we're going to do right now. And we're going to graph two graphs. We're going to graph just the parent functions. And we're going to do that, I just want to get rid of that box, there we go, by creating a table of values. Right? So normally if we're going to graph using a table of values, we'll graph some positive values and we'll graph some negative, we'll plug in some positive and some negative and we'll plug in 0, right? All right, so but if I try to plug in -1, we have a problem, right? Because the square root of -1 is I, and that's a complex number. And this is not a complex coordinate plane. This is the real coordinate plane. So we will not be graphing any complex numbers on that coordinate plane. So we can't use -1 because we can't graph I there. All right, we would need a complex plane, and we're only dealing with a real number plane. So for our solutions, we can only have real numbers. Okay, so we can't plug in anything that's going to give us an imaginary number. Okay, it has to be a real number. Also, when I'm choosing values, if you notice what values of x I chose 0, I chose 1, I chose 4, and actually I'm going to choose one more point. I'll just kind of squeeze it right here. I'm going to choose 9, right? So gee, so what's special about those x values? Well, hopefully you figured out that those x values are perfect squares, right? So I'm not going to plug in anything into x that's going to give me something really difficult to graph. I don't need to, right? I don't need to plug in every single point. I just need enough points to get the shape of the graph. And this would be enough points to get the shape of the graph. And so those are all perfect squares. So if you're going to be graphing using a table of values, you only want to graph perfect squares because they're going to give you y values that are easy to graph, right? Because the square root of 0 is 0, and the square root of 1 is 1, and the square root of 4 is 2, and the square root of 9 is 3. See, all pretty numbers to graph, right? So in your notes, make sure you have this same slide, and so make sure that you plug in those points, and you're going to graph along with me, and you have a coordinate plane there too. All right, so we're going to graph the x and y values, and then we'll connect. So we're going to graph the point 0, 0. We're going to graph the point 1, 1. We're going to graph the point 4, 2. And 5, 6, 7, 8, 9, 1, 2, 3. I think having one more point makes it a lot easier. And I think you can see that this is a curve. Not a very fast growing curve, but a curve nonetheless. All right, notice we have nothing on the negative side for x. Notice that we have nothing on the negative side for y either. We kind of have a starting point, and then our function is growing in one direction and one direction only. Notice that the x, as I go along the function, my x values are getting larger, the y values are getting larger, and the arrow indicates it's going to keep going in that direction. So our domain is going to have a starting point, right? Notice here, and we have a little note here, we cannot graph imaginary numbers on this coordinate plane, therefore the graph stops at x equals 0. So does your domain. We're going to use a bracket because 0 is included. We could plug in 0, right? We plugged in 0 and we got 0 as an answer. But we can keep on plugging in positive numbers all we like, right? And we could plug in all those numbers that I didn't plug in, like 2 and 3 and 5 and 6 and 7 and 8, right? I just chose not to plug them in because they'd give me decimals, and that's a little harder to graph. And I'd rather just graph, the nice easy points. Right? I don't need to graph every single point. So just because we didn't graph them doesn't mean they're not on our graph. So we're going to include every number that's greater than 0. Notice that not only does our domain have a starting point, our range has a starting point, right? So when I plug in 0, I get 0 as an answer. I don't get negative numbers, right? You don't take a square root and get negative numbers. So that means our range is also 0 to infinity because it's going to keep on getting larger. Okay? And so that is our parent function, y equals the square root of x. We're going to graph one more parent function, and that's y equals the cube root of x. Okay? And you'll need to know these for class on Monday. So thank you for watching the podcast. Let's graph the next one, and that's the last one we're going to do. Now here we can we can plug in positive and negative numbers, right? I can take the cube root of a negative number. That's a real number. That doesn't give me an imaginary number. Right? So we're going to plug in negatives. And again, I'm going to plug in numbers, well, first of all, that fit on my graph, right? Because, I mean, we can plug in 1,000,000 if we wanted to, but it's not going to fit on the graph very well. Or we're going to need a much bigger graph. And I can plug in 2 and 3 and 4 and 5, but those aren't perfect cubes, and those are a little harder to graph. And I really don't need to graph every single point to be able to graph the function. These 5 values here, they're plenty, right? So these are the ones we're going to use. And anyway, the next perfect cube is going to be 27 anyhow, and I don't have 27 spaces there. So these are plenty, right? So if we plug in, and again, you have this in your notes, if we plug in -8, that would be the cube root of -8, and the cube root of -8 is -2, and that gives us the point -8, -2. So let's plug all these points in just so you can see how we got our y values. And that is just a horrible looking 8, I have to say. There, that looks better. F of -1 would be the cube root of -1. The cube root of -1 is -1. And f of 0, right? So remember, and by the way, if you're not sure what f of 0 and f of -1 means, that just means the value of our function. And it's another way of saying x, except everyone now knows what I plugged in. So that's what's nice about using function notation. So the cube root of 0 is 0. Matter of fact, the any root of 0 is 0. Just like 0 to any power is still 0. All right, so f of 1 is going to give us the cube root of 1, which is 1. And then f of 8 is the cube root of 8, which is 2. Right? And those are the same values that we have over on the side. And let's graph those. Right? So we have the point 0, 0, 1, 1. And I'm going to graph this point here, -1, -1. Now you would never want to just graph those 3 points. If you look carefully, they make a line. Matter of fact, those 3 points there will always make a line. Even if we transform our cube function a little bit, those 3 are going to be in a line. So never just graph those 3, or you're going to think that you have a linear function here. That's why we always want to graph 2 more points when it comes to the cube root. Right? Always want 5 at least. Right? So now 2, 3, 4, 5, 6, 7, 8, 1, 2 goes right there. And 2, 3, 4, 5, 6, 7, 8, -2 goes right there. All right, now you can see it's not a line. And hopefully you see it's kind of this elongated S. Right? So let's connect our points. It looks a little like the cube root if it was laying on its side, doesn't it? Right? And my function should be going down. Again, it's going to keep on going down, right? It's not a straight line. And I hope I show that. I have a tendency to want to curve it a little bit. But that function is going to keep on going. Though it goes faster in the x, right, it's going to keep on going down in the x and y on the left-hand side. And on the right-hand side, the x's are going to keep getting larger, and the y's are going to keep getting larger ever so slowly, right? If I plug in 27, for instance, I'd have 3, right? So that's a larger y value. If I plug in 64, I'll have 4, right? And so forth. So it's going to keep on growing in both directions. And just like y equals x cubed has all real numbers as its domain and range, so does the cube root. You can take the cube root of any number. Some of them are prettier than others, but you can take the cube root of any number. Right? And so that is the end of this podcast. That's all I wanted to get accomplished, is introduce you to our friends, the square root and cube root functions, and take a look at the parent graph. We'll be graphing these more in class on Monday. Thanks for watching the podcast. Bye.